Then you can keep a copy for yourself, but put your name on one and turn it in.
I'm stuck getting gas in line. I'm stuck in line getting gas for it right now. So.
All right, your name's on this? Okay, that's better than nothing. Okay, I get it all? Yep.
Yeah.
Okay. Okay, so there were 4 problems. I will do one of them, only one. So let's take a vote. How many of you need me to show you number 1? Okay, number 2, that was the guy running around the thing. All right, 3, that was the, oh, that one, yeah. Okay, 4. Okay, so on number 2, let's do number 2. So a man runs around a circular track, constant speed, 9 feet per second. That's his linear speed as he proceeds around the circular track. Was he running clockwise or counterclockwise?
Doesn't matter.
In your mind, what was he doing? Did you?
Counterwise.
I was doing counter in my mind, but it doesn't matter. Okay, we'll go clockwise. All right, so the guy's running around 9 feet per second is his linear speed. It takes him 2 minutes to do 1 lap. That's very important information. That means it takes him 120 seconds to run around this track, right? 2 minutes is 120 seconds. So the question is, what's the distance he travels? I know, but I'm asking you, the distance in 2 minutes that he travels is what? Is 9 feet per second times 120 seconds. So you had to realize you had to convert from minutes to seconds. So your seconds cancel. So he's gone 1080. Is that what it was? 1080 feet. And in that case, you could look at the circumference of the track as being 1080. Or if you want, you could use S equals R theta. Either way, right? S equals R theta.
R times theta, right?
R times theta. So I'm going to use that one because it's the more general formula. So what we know is S equals R theta. S is the arc length. It's the length of the segment here that's traveled when you're given a radius of R and an angle of theta. Now in this case, he went all the way around, right? So theta is 2 pi. And that's your circumference formula, right? Circumference is 2 pi R. So this formula, S, we know his distance, right? It's 1080 equals the radius, which is what we're trying to solve for, and we know the angle is 2 pi. So all you have to do is divide 1080 by 2 pi, and it's some decimal. I don't know. 343.7?
Yeah, that's your diameter.
But that's your radius, right? You have to double that to get the diameter? Oh, you're right. Sorry. So is 171.88 feet is your radius, and then double it to get your diameter. So that was just to make sure you're paying attention to the wording, right? Make sense? Double that, that's the answer. The answer number 1 was 1 radian.
Yes.
You didn't have to put radian. You could just put 1, and you kind of get lucky because you don't have to put radian, but understand that it's 1 radian. And I won't go through the whole thing, but I will show you this. With this triangle, this I said was 6, right? And what you can determine just using a little bit of algebra is that this length right here is 6. And the whole idea, remember when you got up here and we did this problem, we measured out 6 and then we went around 6 and we said, what's that angle? It's 1 radian, sorry. So since this is 6 and that's 6, yeah. Okay, today we are going to get into 7.3, which is computing the trig functions of any acute angle. So last class what we did was we said, all right, if we have triangles, right triangles, we can determine the 6 trig functions based upon those right triangles. Now, let's act like, well, we're not going to act. Let's look at it from a different perspective. If we're given an angle can we determine the six trig functions from those angles? So we're going to start off with the common angles, and then after we do the common angles, we're going to go to the more general, just any angle. But today, we're staying with acute angles. We will move out of acute angles next week. Acute meaning between 0 and 90, right? Okay. Or 0 and pi over 2, if you're looking at it in radians. All right, so let's start out with the common angles. The common angles are 45, 30, and 60. I put them in that order because that's the way I'm going to go after them. I'm going to do 45 first, then I'm going to do 30 and 60. So the question would become, what's sine of 45 degrees? What's sine of 45 degrees? What's cosine of 45 degrees? What's tangent of 45 degrees? All 6, right? And then same thing for 30 and same thing for 60. Now, what you have to realize or visualize is that you do have a right triangle, and you're given, let's say for this, 45 degrees, and then you're asked sine of 45 means what's the ratio of this side over this side. And notice that if I extend this triangle out and make it bigger, we have what are called similar triangles. There's a smaller triangle and a bigger triangle. They both have the same angles, don't they? 45, and then there's a 90 on this one, 90 on this one. So these angles are also the same, right? And it turns out that if we split this up into the small triangle and the big triangle, right, like this, these being what we call similar triangles means that the ratio of the sides is always the same. So whatever the ratio of this side divided by this side is, it should be exactly equivalent to the ratio of this over this, because they're similar triangles. So if we know sine of 45, that should hold for any triangle. As long as the angle is 45, sine of it's always going to be the same answer every single time. All right? So now let me draw a better 45-degree angle. That was just to kind of get you to think about similar triangles. All right, if I draw a triangle that has a 45-degree angle in it, like this, then what is the measurement of this angle up here? It's also 45 because they have to add up to be 180, right? 90, 45, that must be 45. So 45 comes just by our knowledge of triangles in the Euclidean plane having to add up to be 180. Now, if two of the angles are the same, that means the length of these two sides has to be the same also, right? So I'm going to call this A, and I'll call this, well, I'd normally call it B, wouldn't I? But because it's the same measurement as this one, I'm going to call that A, right? And then this hypotenuse, let's call it C, right? With me? Now, we know that A squared plus B squared equals C squared, don't we? We know that? But let's write that down here. A squared plus what? A squared again must equal C squared. So I'm using the Pythagorean theorem from last class. This is two of the same thing, right? So 2A squared must equal C squared, right? That's a relationship we have between A and C. Now, let's ask ourselves this question. I'm just box this up. This is a relationship we have. Now, if I ask you what's sine of 45 degrees, you're going to tell me based on the picture it's A divided by C, right? That's what you're going to tell me? It's opposite over hypotenuse. It's A over C. And I agree with that. But we also have this relationship. So what I'd like for us to do here is try and see if we can get that to look like A over C. So how could we make this look like A over C? How about divide both sides by C squared? Is that fair? So 2A squared over C squared would equal what? 1. And then let's get this 2 out of here. How about I divide both sides by 2? So A squared over C squared equals 1/2, right? You all okay with that? And now I want AC, right? Not a squared over c squared. So how about I square root both sides? So when I square root the left side, square root the right side, technically I'm supposed to do plus or minus, right? But it's acute, right? So this ratio should be positive because this divided by this, these are both positive numbers. We should have a positive answer here. So A over C should equal just square root of 1 over 2, right? Now I'm going to split it up into two fractions, root of 1 over root of 2. So what's the root of 1? 1. And what's the root of 2? Just root 2, right? That is the answer. But that's not the way they're going to have it in a book. Because remember I told you the authors of these books are going to want to rationalize the denominator. So they're going to multiply top and bottom by root 2. And when you do that, you get A over C is root 2 over 2. All right? So do y'all see what I did? The 45-degree triangle allowed me to create a relationship. Then I asked myself, what's sine? Once I knew what I was looking for, I took that relationship and kind of forced it out and got the relationship here. And then that's my answer. All right? So now you can store this in your memory. Sine of 45 degrees is the square root of 2 over 2. Always. That will never change. All right? Sine of 45 degrees is root 2 over 2. Now, what about cosine? What would be the only difference I would have if I was trying to do cosine of 45 degrees? Cosine of 45 degrees, I would, instead of doing this side over this side, I'd be doing this side over this side. But it's the same thing, right? A over C again. So this should also be root 2 over 2. Right? Okay. Now, let's go after the third one, tangent. What's tangent of 45 degrees? Well, off of this triangle, tangent is the opposite over adjacent, right?
1.
A over A, that's 1. And now the other three are just these three flipped. That's all they are, right? Because they're reciprocal identities. So cosecant of 45 degrees is the reciprocal of sine. So that's 2 over root 2. Now, do you think they're going to have that like that in the book?
No, it'd be root 2.
No, they're going to multiply the top and bottom by root 2, right? That's what they're going to do. So let's go ahead and do that. If I multiply the top by root 2 and the bottom by root 2, something kind of strange happens. On the top, you get 2 root 2. And on the bottom, you get 2, and then the 2's cancel, and all you get is root 2.
You could just flip the one that you had over there before you rationalize the first one.
Yeah, I could have flipped this one. Just All right, and then secant. What about secant of 45 degrees? Same thing, right? Same exact, it would be the same thing because we're going to be flipping over cosine. Flip that cosine over, and it's the exact same thing we just did. So secant of 45 degrees is also root 2. And then what about cotangent of 45 degrees? You're going to flip over 1, right? So 1 over 1 is flipped. It's still 1 over 1. So you get this. All right. Now, that's 45 degrees. So you want to get to a point where if someone says, hey, what's sine of 45 degrees? You're just like root 2 over 2. It's just automatic. Cosine of 45, root 2 over 2. Tangent of 45, 1. Memorize it, I guess is what I'm saying. All right, let's look at 30 degrees. Okay? Or let's do 60. If you do 60, it's easier to get it. Start with 60. So I have to erase all this, right? Because these relationships no longer exist, right? With a 45, we called both sides A, but we can't do that with a 60. So here's what we'll do. For 60, I'm going to draw a triangle, right triangle, that has 60 degrees in it. And let's call this side A, this side B, and this side C. Do you see how this is not at all going to work the same way? Because we're not able to get it down to just two variables. And when I'm trying to ask this question, what's sine of 60 degrees, I need A over C, right? Sorry, I drew my triangle different. So it's actually what here? B over C, right? Opposite over hypotenuse is sine. The problem is I can come up with a relationship between all three of these, but I'm not going to be able to get that root 2, 1 over root 2 to come out. You could try it yourself. It's not going to work. So here's what we do, and this is just the standard way of doing this. What we do is we draw a mirror image of this triangle like this. All right, let's draw that triangle. Now, what is the angle measurement right here? What's that? 30. That's 30. So this also must be 30, right? And this must be 60 degrees. Now this is an equilateral triangle, right? So what can you tell me about this side right here? What's the length of this side?
A.
Right here is A. And I'm talking about between here and here, that's A, right? And then between here and here is the other A. Can you give me any relationships here that you have? This is what this looks like now. 60, 60, 60, right? What type of triangle is this? Equilateral triangle. All sides are equal, aren't they? So when I drew this, I was very clever in drawing it because I created an equilateral triangle. And that means that this side here is the same as this side here, right? So this side right here is 2A. This side is C. So I have a relationship now that 2A equals C, right? Y'all agree with that? Say again?
B is root 3.
Okay, so how are you getting B is root 3?
I'm not doing the thing. That's just remember that.
Oh, off of a 60. Okay, so I'm going to get to that, but let's see where it comes from.
Just 1, 2, and root 3 the sides for this side number.
Yeah. How about I do this? How about I kind of start this over? Okay, now that we have a relationship, right? I've created a relationship. Let's go back to this first triangle right here, and I'll go ahead and just redraw it. I called this side here A, this was 60, this was B, and this was C, wasn't it? But what's C?
2A.
2A. Now, use your Pythagorean identity. What can we say? A squared plus B squared equals 2A squared. Agree? And that means that A squared plus B squared equals 4A squared. And subtract A squared from both sides, and you get B squared equals 3A squared. And that is a relationship now that I can use that somehow connects these sides together. All right, see if we can get this now. How could we go about this? Can I write that? What did I do from here to here?
Divided A squared.
Divide both sides by B squared, right? Divide this side by B squared. hold on a second. I don't know why I did that. Hold on. Divide both sides by b squared, and then take the square, divide both sides by 3, and you get 1 over root 3. That's what I meant to do. I'll show it. 1 equals 3a squared over b squared. So I divided both sides by b squared, right? Then divide both sides by 3, right? And then take the square root on both sides, and you get this. I'm just doing that to have that relationship there for us. Let's go back up to this, though. Sine of 60 degrees. What is that in terms of our triangle over there? Remember, we replaced c, didn't we? So this is really b over 2a, right? Any ideas on what I can do here? Look at this right here. I know what a over b is, right? A over b is this. I want to know what b over a is. So what can I do? Just reciprocal, right? If I flip this and flip this. So what is b over a? Just root 3? So do you agree that this would become 1/2, that's the 2 on the bottom, times root 3? Because that's your b over a. And that's just root 3 over 2. I know this I'm deriving where these come from, okay? You don't need to remember how to derive them. At the end of the day, all you need to know is sine of 60 degrees is root 3 over 2. But if you want to know where it's coming from, this is where it's coming from. It's just some manipulation of triangles and finding relationships, and you get to the end result. All right, so sine of 60 degrees is the square root of 3 over 2. Burn that into your brain. What about cosine of 60?
1 over 2.
So where are you getting that from?
Because the other side is 1.
So cosine of 60 degrees is a over what? 2a. A over 2a. And the a's cancel. And all you get is 1/2. That's nice. That didn't really require any manipulation at all. Once you have those, you pretty much can get everything else.
Including the 30-degree ones.
Including the 30s, yep. So let's just keep going here. What's tangent of 60? Now in the last problem I did with 45 degrees, when we did tangent, we just did this over this, didn't we? This time I want us to use an alternate definition of tangent. And I showed you this last class. This is the same as sine of 60 over cosine of 60. Remember that identity? Tangent of an angle is equal to sine of the angle over cosine of the angle. That look familiar? Tangent is sine over cosine? All right. So we know what sine of 60 is, right? It's over there. It's what? Root 3 over 2. And I'm going to divide that by cosine of 60, which is 1/2. And what happens when I multiply the reciprocal? So all you get is 2 root 3 over 2, and the 2's cancel. So just root 3. Just root 3. So tangent of 60 degrees is root 3. We've got 3 of the 6. What about cosecant of 60 degrees? That's the reciprocal of sine.
2 over root 3.
2 over root 3, right? Which I said would be a totally acceptable answer. But the book's not going to do that. They're going to do the rationalizing the denominator. So they're going to multiply both the top and bottom by root 3. And they're going to get 2 root 3 over 3. You like that better? No. Oh. And then secant of 60. This one's pretty straightforward. It's just 2, because you're just reciprocating cosine. Flip it, 1/2 becomes 2. And finally, tangent of 60 degrees, cotangent is what I meant to say. Cotangent of 60 is 1 over root 3, right? Which you could rationalize, that would become root 3 over 3. All right. Now we're going to have a completely different way of learning these and memorizing these when we get into this section on unit circle. And I always tell my calculus students who come to me in Cal 1 and they still don't remember what cosine of 30 degrees is I always go back to the unit circle and I show them using the unit circle because I think that's the best way to remember these things. But we're introducing the idea here, start to like kind of remember them, and then once we get to unit circle, hopefully we can just completely nail it down and you won't have to, you know, think about it as memorizing a table of things. Instead, it'll be something you can visualize, like a circle, and it'll work out, I think. Hopefully, you'll like that. Okay, let's not go through the derivation. Let's just write down the values for 30 degrees. That way we have a complete list in your notes of all of the trig functions at the common angles. All right, so if you have sine of 30 degrees, cosine of 30 degrees, tangent of 30 degrees, sine of 30 degrees is root 3 over 2, wait a minute, sine 30, 1/2. 1/2, root 3 over 2, and then this one, why don't you tell me what that one is? Notice that sine of, what was sine of 60? Root 3 over 2, right? And cosine of 60 was 1/2. They've switched places. All right? That's a relationship between 30 and 60, is that whatever sine is here, right, it's the same as what cosine is at 60, and vice versa. All right, so tangent of 30, you're just going to take this one and divide it by this one. So what happens when you take 1/2 and divide it by root 3 over 2? You have 1 over root 3, which is the same as root 3 over 3. And then the next 3, are y'all okay with the next 3 on your own? It's just flip those over. We've already done flipping. If there's anything I want you to walk away with what I've shown you here, is just, hey, you know, now you've seen where they come from, all right? And then please remember at least the minimum of what you need to know is, I'm saying the minimum of what you need to know like for the next 7 days. After that, you need to know it all. But at least in the next few days, work on knowing sine and cosine at 30, 45, and 60. All right. Now, those are the common angles, but this section is titled Computing Trig Functions of Any Acute Angle. Actually, the book doesn't have any in there, but I put it in there because that's really what we're going to do. We want to be able to do this for any angle. So what if we have this now? What is sine of 13 degrees? Let's try and understand what this is saying first. It's saying if I draw a triangle and I call this angle 13 degrees, call this side A, this side B, and this side C, then sine of 13 is asking me for what? It's B over C. It's asking me to please explain or please give a numerical quantity to the ratio of the B side over the C side. So you tell me, is sine of 13 going to be a larger number or smaller number than sine of 45? So this side, if you compare this to a 45-degree triangle, which would be in here, right? Something like this. then the ratio of this side over this side should be smaller, larger? What do y'all think? Let's do it this way. The illustration will be the same. What if I do this? I keep this length C. So this is C still, okay? But now this is 45 degrees right here. Do you see what B is over here? B is this? B is larger, isn't it? So the ratio of B over C should be a bigger number because C isn't changing, right? In both of these pictures, the hypotenuse is C. So if we get a smaller side here, it should be a smaller ratio. So sine of 13 should be smaller. But what is it? I mean, what is it? And the problem we run into with an angle like 13 degrees is that I can't do anything fancy like we did with 45. And I can't do anything fancy like we did with 60, where I mirror the triangle over and come up with a relationship. There's just no way to do it. So what we need is a calculator. Now, the calculator is doing something that for now we're gonna just not get into what it's doing, like how it's computing it. Right? We're not going to talk about that. Not until we get into where we talk about the sine function as a function with its graph. Then we can get more into the mechanical part of what your calculator is doing. For now, we're just going to trust that the calculator is going to give us the correct ratio. So sine of 13 degrees, go ahead and get your calculators out. And make sure that you are in degree mode. If you don't know what I'm talking about, when I say degree mode and radian mode, then you need to let me know so I can show you how to switch over. Hey, on your test, you can only use a calculator, you can't use your phone. So don't get used to using your phone and then come in here for the test and then you can't have the phone, all right? So make sure you're in degree mode. Pardon? 0.225. We use the calculator. And you get sine of 13 degrees is approximately 0.225? Okay. That means, make sure you understand what this means. If you draw any triangle with an angle of 13 degrees, the ratio of the opposite side over the hypotenuse must always be 0.225. So if I extend this triangle out, make this longer, make this longer like this, and drop it like this. Then if I say, hey, what's the ratio of this side divided by this side? It's going to be 0.225, no matter how I draw the triangle. So that angle tells us a lot about that ratio, doesn't it? The calculator is telling us a lot about it. Good? Okay, I have another question here. What is sine of 0.5? And I think I'll put the 0.5 in parentheses like this. I haven't been doing that. I've just been writing 30 and 60, right? So like when I write sine of 30 degrees, I could have written it this way, but I didn't. The parentheses is kind of to stress the fact that this is a function and that this is the input of the function. Does anybody know what you call the input of a function? There's a mathematical name for the input other than input. No? Okay, that's good. I will tell you. If I write sine and in here I put something like this, or I write cosine, I put something in here, or tangent, this in here, those are called the argument. It's called the argument of the function. I spell that right? No, right? Too many E's? Oops. That's why I'm a math major. I think I got to that class in grade school somewhere where they're like, I before E. You know, when you're writing words, I before E except after C, unless it sounds like something. I was like, what kind of rule is that? You know? The rule should always hold, right? Not have all these exceptions. So
It'll help you spell received.
yeah, there's certain words it works for, but others it doesn't, right?
There's lots of caveats in English language.
That's why I don't like English.
Yeah, I'm before you except after C. That's what's
All right.
and also weird.
What did y'all get for this? Let me erase the 30. Sine of 0.5. What'd you get?
0.009.
Approximately 0.009. Anyone have anything different? Did you switch to radian mode?
Nope, still there.
Then it's wrong. This is incorrect. Okay, did I put sine of 0.5 degrees or just sine of 0.5?
No.
Ah, see? These are the things you have to pay attention to. That's why I'm showing them to you. If I put degrees up here, then this answer is correct. If there's no degrees, what did I say? If there's no degrees, then it's implied that it's radians, right? So this is not right.
0.479.
It's approximately 0.479. All right, so that's when it's very important to pay attention to what you're doing in your calculator. If you're going to be using a trig function, sine, cosine, tangent, cotangent, secant, whatever, all of them, right? If you're ever like going to type that in, then put a number inside. You need to know if you're in radians or in degrees, if the angle is given to you in radians or degrees. Okay, good. All right. Wow. So there's not a whole lot in this section more. I'm not saying we're done for the day, okay? I know. Man, you suck. I was thinking about a project that we could do, or like a little activity we could do. I have it here, but I'm debating on whether or not I should actually give you an example first. I'm afraid if I give you an example, then it's going to give away the activity too easily. But let me try. Let me try an example that doesn't exactly like give it completely away. All right? So let's say we have a situation here where we have a river. Okay? And we're standing at a point on the shoreline over here. And we want to look at a point directly across from us. And we want to know how far away that point is. But these are, I was going to say like piranha infested, but there's not really piranha infested waters like nearby. So let's just say these are highly contaminated waters that you don't want to go into. Well, contaminated with like human waste and just nasty, chemicals, and that's more applicable to real world stuff, right?
3 Mile Island. That's where we are.
All right, so we want to measure the distance across this river. This is a top view. This is my river. I would like to measure the distance across that river, but I can't actually physically get to the other side. So, what can I do? Imagine that you're standing on this side, and what you have with you is a tape measure, okay? And that's it. When I was in high school, my professor used to do this. He used to go like that. And it would always wake people up. Okay. You good? Okay. But he used to be, this was like private school, so he would like come up to you with a big book and slam it right next to your head. You'd sit up and go, shit. Okay, don't sleep in here. It's 2 days in a row. I've let it slide before, but you should get 10 points off your next test for that. That's what's in the syllabus. So I'll give you an opportunity, even though you were sleeping. Because I gave you the opportunity the other day too, right? So I'll give you an opportunity to let us know what you are thinking, or just concede.
You're trying to find the distance between one thing to the other?
Yep. All you have is tape measure. And you can't go across.
How many significant features is this statement?
Let's just say it's like a 25-foot roll, standard tape measure. And
So we can't go.
let's say you can measure angles, okay? You can measure angles. Like you could use maybe a protractor or something like that.
So we use a C point and then from there
Any ideas?
you can triangle for one bank and then you create a calculation across it.
Triangle. So
2 points on the bank that you're on.
okay, so just arbitrarily pick some other point on the bank. All right, so I'll pick this point right here.
C point.
C. Okay, and then
What?
you can measure from A to C.
I can't reach across the river correctly, or no?
But you can still get the angle.
You cannot go over here or like extend your tape measure across.
So,
Yeah.
but A and B are perpendicular to each other. Perfect.
Okay, so yes, you've come directly across, so you can imagine that you are directly across from point B. Yes.
So now we can use the theta, we can use the property to find that, the theta. I'm trying to remember the formula, hold on, excuse me.
You're on the right track. There's no formula. Hold on. There's no formula. What do you got?
Well, you just make, because you can use the protractor so you can get the angle of ACB.
Okay, so you're saying if I extend this and imagine a line going across here, that I would actually be able to measure roughly with the protractor that angle theta.
Yes.
And I also know,
That because you know that angle and you know that distance, you can
You
solve
can now
this.
solve it.
right? If I know this, I can measure this distance because I can stand here and measure it out, can't I?
Yeah.
So let's just say, for the sake of demonstration, that we actually do that and we measure that, and we measure it to be 38 feet. All right? I'm making this up.
Well, if you were sensible enough to make theta 45 degrees, then you know the distance across the river is also 38.
Exactly.
That's right, if you picked your theta, but it might be that you're limited on how far you can go. Like maybe this is a mile, but you can only go so many feet, So it would be good to pick something convenient, but sometimes we don't have that opportunity. This is the way you can make rough measurements of like distance from here to the moon. Like you can do an approximate distance if you have accurate enough measuring instruments. And this is the way it was done way back then. Way back in the day, they would measure the distance. They did a little, well, let's talk about that later. All right, so let's say we come in here and we measure this angle to be roughly 35 degrees. It's not one of our common angles, right? Now, which side are we interested in finding? We haven't labeled it, but from A to B, right? From A to B. Let's just call this D. How about D? Little d for distance. All right? So you see what I've done here? Now, with this triangle, which sides do we know relative to the angle we know?
We know
Adjacent, and we want to know the opposite, right? So the relationship we have here, we're interested in opposite and adjacent, and that's tangent, isn't it? In fact, if I ask you to look at this right triangle and I ask you what's tangent of 35 degrees, you would say opposite over adjacent, right? So I'm going to write that down. Tangent of 35 degrees should be opposite D over adjacent, which is 38. And tangent of 35 degrees, unfortunately 35 degrees is not a common angle, right?
Yeah, well,
So you can use your calculator.
you still get 0.7.
0.7? Are you in degrees or?
Number something you can round, so you go to the thousandths, you stay at 0.7
So are you in degrees or radians?
degrees.
You went back to degrees? Okay. So making sure that we're in degree mode on your calculator, put tangent of 35, and you said again what?
0.7.
Yep.
0.7, okay. Is approximately D over 38, right?
30, 27.
Now just solve for D. So multiply both sides by 38, and you get
26.6.
26.6. So your tape measure just couldn't quite make it across. 26.6 feet is approximately the distance across. So this is pretty remarkable because we have the ability to measure the distance from one location to another without actually physically having to go out there and do it, right? So when you see those surveyors out there and they've got the, on the tripod, they've got this little, it looks like a camera and stuff, and they're looking across, and they've got some person standing on the other side with another point, like holding something. They're triangulating. They're trying to find out distances without actually having to go to those points. And that camera is very, very precise in its measurement of angles. Yes?
My major used to be construction.
Uh-huh.
But for that, they're just trying to see the level, or like the distance.
They're also shooting angles too.
Yeah.
Yeah, I'm not saying there's certain instruments that do certain things, right? Depending on what you're trying to do, right? So some of them are doing elevation changes, some of them are doing angles.
They use a program
Distances.
like that to connect like tunnels back in the day. Like people would tunnel from like two sides of a mountain, they'd be underground.
Mm-hmm.
And they would just be measuring each other, and they were so accurate they could meet each other
Mm-hmm.
in big points.
Yeah.
Just using those angles.
Yeah, nowadays the technology is there where we don't have to do this sort of thing. We can use lasers and bounce off and get a,
GPS.
GPS. But GPS is even using geometry, right? It's using geometry to come up and solve for an unknown. All right. So one project we could do that I was thinking of was to see if we could go out and try and measure the distance across the lake, the little lake moat, whatever we have here. But if we want to stay inside and not be as interesting, then I was going to see which group could measure the length of their table the most accurately. And so the idea is that you can be on this end of the table. You're not allowed to measure across. So this is our river, and there's the other end of the table. And you're trying to see which group is going to come up with the most accurate measurement of the length of the table. Do y'all want to do that? Okay, so but there's a little catch to it. All I'm giving you is a protractor and an 8.5 by 11 standard sheet of paper. That's all you get. Okay? So I'm gonna see what y'all do with this. I only have one protractor for each group and one piece of paper for each table. Yeah, so we're gonna measure the long way on the table. All right? And some of these tables are wider than the others, but they all have the same length. All right? So if you want to move to a wide table, you can. However you want to do it. You can use both of them, but you're trying to go from here to there. Yeah. One or just one from here to there. 8.5 by 11. 8.5 inches by 11 inches is this sheet of paper. Now here's the thing. I will allow you to, like, you can have a group member on the other side of the table, okay? You can have a group member here and a group member over there to try and get your angle. Because, like, if we were trying to get from point A to point B, we would need a reference point on this side, right? So if you want, you can have a group member on the other side. What you cannot do is just start, like, laying out the piece of paper, like there's 11, 22. I don't want that, because you're not allowed to go across the table. Understand? Okay. I have a feeling y'all are all going to get pretty close. Did I not give y'all one yet?
So we're not allowed to measure.
All right, there you go. That's what you get. You can work with a group, all right?
Can't lay it on top. It already fell in the river. You can't lay it. Yeah, you can't lay it on top. It's just that way. Go ahead and pop it. Yeah. We can't lay it on top. Just find a good expert.
I'm going to give y'all about, I don't know, 15 minutes to see how far y'all get with this. Write on. You can write on the table with pencil. Yeah, do it with pencil because I don't know if the expo will come off that well.
Yeah, you're right. Measures the angle from, and that's 11. 11 inches. Not the, we're already taking the outside. Wait, hold on. Why go all the way there? What angle did you I know what you're saying, but you're right. So we have, let's try. Yeah. There's probably something we could possibly have. Call this the distance.
If I need to do an angle from, that's about 65.
Okay, yeah.
Yeah, that's the 11.
I just put the paper to like.
So like,
So we just both take.
I just like, I don't.
So we need.
Oh,
Yeah, so we need this. So we use this.
wait, how do you?
90 millimeter angle. Oh, actually, no.
What if we need, so if we use just 45 on this 90 degree angle, tangent 90, so it's opposite of adjacent.
Wait, I think.
So what if we just use tangent, it's opposite over adjacent. What if we use just 90 degrees as a tangent, right, so it would be tangent 90.
That was 11 centimeters, right?
Inches. 11 inches by 8.5 inches.
Oh, no, wait, no. Wait, don't be on one. Never mind, we can't do that. Don't, wait. Two over adjacent, so we can just use sine.
2 point what?
Let's just try it out and see what number we get. If it looks like a convincing number, then we'll agree or
I feel like I should just, I think I need to stop wearing that jacket in here. That's what I think is doing it.
It reminds me of your like blanket at home or
Yeah,
something.
it just keeps me warm and I start getting tired and
Do y'all have anything going on here?
I think
Yeah, we
You got something?
came up with 64.2.
64.2. Okay, so tell me how you did it.
Okay, we used the paper
Okay,
to get a rough estimate of this distance.
okay,
And then we, I guess, kind of like use the paper to kind
try and line
set it
up the corner.
And 70 was too much, 60 was too little, so we went even. in
Okay.
between. And then we put in tangent of 65, and he got
Okay,
2.14, and we multiplied by 30.
okay. So here's what let me suggest this. Move this table a little bit down. Try it. You estimated this distance, right?
Yeah.
Okay.
By measure with the paper.
Yeah, so why don't you try this? Do this, that's what, 11? Then that's 22,
That's what I did,
right?
and then we turned it sideways because this one gives.
But I'm saying
Yeah.
you may have lost some accuracy by estimating that. So why don't you do like 1, 2, 3, 4, and you'll know what 44 is for sure, right?
Okay. Yeah.
You see what I'm saying? You're not estimating anything. And then run that angle again and try it again. See how far off you are from this.
Okay.
Okay? I mean, what you did is fine, but I'm just saying try something else, see if you get a better measurement. If your group gets an answer, let me know.
How did you pick 10 35? Like, where did you get 10 and 35 from?
The fact that you have, if this was our angle, you have the opposite and adjacent side, right? So we use tangent because tangent's opposite over adjacent.
Okay.
If you had the opposite side in the hypotenuse, then you would use sine.
Okay.
It all depends on what you know and what you're trying to find. You have something yet?
I mean, I know that's not exactly right because it's a 6 foot table. It's a 6 foot table, but
Okay. So what was your method?
well, this is about 18 inches
Okay.
approximation because 11 and then almost all of the 8.
Okay.
So it's about 11 and about an inch and a half off. So out of
Okay.
8.5. And then, so then you have the tangent of this over that, since you need this,
Mm-hmm.
and this divided by 18.
But what was your angle?
About 73.
So you just kind of eyeballed it? Okay.
I know that's not exactly right because when I
No, yeah, it's okay that it's off. This is an approximation.
it's like right when I saw that this being 18 and about being 18, and then I saw about that, I was just like, oh wait, this is a 6 foot table.
So here's a question for you. What would give you more accuracy? Taking a small number here or a larger number?
A large number, I guess. I just only did to here
So why would that give you a better?
because you were able to see the angle probably better.
Okay. Well, I don't know. Can you see? It's pretty much the same, right? I mean, like you're going to see that the same way you're going to see this, right?
And you need the long way across, so you're gonna have to look all the way across anyway.
Yeah.
So you're gonna have to guess something.
What I'm getting at is, can you rationalize in your own mind why just using this down here, that, and looking is not a good idea compared to this and looking?
Because when you have a bigger number, it's more easier to accurately.
So you gain or lose accuracy. I just want you to think about why you would, though.
You gain more if you have more of a number to work with.
Okay. So when you're looking at tangent of some angle is the d, which is you're trying to find, right, over whatever you called this thing, right? Adjacent. Let's call it A. So here are the things that you know, right? You know the adjacent. You're going to be able to measure that, and you're going to be able to measure that. Okay. So I guess what I'm getting at is this is going to be a number,
Yeah.
right? No matter what, you don't have control over that. But you can control this. This you can control, how far you go. If this number's too small, right, then you think about this as being, this side's going to be a ratio, right? Let me write it as a ratio. A number over a number. It's a number, but it's a number divided by a number. And this side is d over a. Think about this. If I multiply both sides by a, right, then this is what I have.
Yep.
The bigger this number is, right, it's going to affect this. But if this number is too small, then small changes here are going to have dramatic changes on d.
Yeah, whereas small changes on a big number.
On a bigger number, a big change here is going to have a smaller impact on d. So you would want to go as far as you can to be able to go across.
But when you don't have a choice.
Yeah, exactly. I just want you to think through that, though. Like if you get it, fine, but try and extend the idea a little more. Like what? Yeah.
Got it.
Okay, you got something? What'd you get?
We got a tangent. This is 63.45. Don't ask us how we measured tenths of degrees. We're very good like that. I had a Navy helmsman here.
You had
aviation electrician.
you have
for the Navy,
you
so-
have your degrees measured to the 100th.
We were
Wow,
good.
that is good stuff. That is good stuff.
We were actually able to create a good marker base for how
Okay.
we were.
So what did you get for B then?
What was our B answer? This was 45. 60.03.
60.03.
Yeah.
Wow, that's pretty good.
We even compensated for the plastic bumpers.
Yeah. So are you including it? Are you including the plastic?
Yes,
Okay. 60.03. What did y'all get?
I have no idea.
What did y'all get for this? What did y'all use here? What was
We marked it at 11.
11? Okay. And then you went to what? That corner? And then what was your angle here?
See, I told you to approximate the angle.
You have to approximate this angle. You have to figure out the angle from here to that corner.
I was gonna mark right there.
So y'all didn't get an angle?
He said let's use 45 degrees. It's just a long angle. No, you can't use 45.
Okay, first, and then I realized, yeah, because it has to be the same measurement.
I know, that's what I said.